Okay, here we go. Welcome to Lab 2. Lab 2, we're going to be doing rectifiers, and we're doing this in two parts. We're doing a half-wave rectifier first. We'll do the calculations and then take the measurement, and then we'll do a bridge rectifier, which is a full-wave rectifier. And again, we'll do the calculations and then we'll do the measurements. So starting with the half-wave rectifier, the half-wave rectifier looks like this. You have your AC voltage source, and then you go through a diode, like so. And then we're going to have a smoothing capacitor, a filter capacitor, and we're going to have finally our load. So the way this lab is set up is that our load resistor is going to be about a 4K. And we'd like to have, coming out of here, 5 volts DC with 100 millivolts of ripple or less. Okay, so what we're going to do in terms of waveforms is, let's get some waveforms. This is our source voltage, V sub S. That is going to look like this. Okay. And then what we're going to get coming through after the diode is going to be the positive part of the wave. When Vs goes positive, the diode goes into forward bias, the current goes through. When Vs drops negative down here, the diode goes into reverse bias and blocks it. So what we would see on the output without the filter capacitor is going to be something like this. Okay, so what we've got is the positive lobes of the signal coming through, the negative lobes get blocked. Okay, you'll also notice there's a little bit of a loss here. That difference there is the 0.7 that you're going to see across this diode. This is going to be a silicon diode. So the peak here is going to be 0.7 less than the peak of Vs. Okay, and the next thing we're going to do is we're going to look at the capacitor value. And what it's specified is that we'd like to have under 100 millivolts of ripple. So that means that, we'll do this in a different color, hopefully the colors come through, is that this is going to decay like so in one cycle. And this drop here, from there to there, is 100 millivolts. I should have used a better green marker. Okay, so what we see with that is that the capacitor plays a big role in this. We can't really change the load resistor. That's a spec, that's given. Diode's a diode, it's going to do its thing, and the Vs is the Vs. So the only control we have over the actual ripple is the value of the capacitor. If the capacitor is too small, what will happen is we're going to get much more decay. Then it's going to have to build up again. And if the capacitor is bigger, we're going to get less ripple. But the downside of that is now we have a very short interval of time here for the capacitor to charge up. And that puts a lot of strain on the system to put out so much current in so little time. So to evaluate let's do the value of the source voltage first. If this is going to average 5 volts plus with 100 millivolts of ripple, let's make the top level here 5.05. And we're going to make the bottom here 4.95. So that way we have from there to there, you're subtracting, you have 100 millivolts of ripple, and we have an average value of about 5. So if the top value here is 5.05, we would like to set the amplitude of Vs to be around 5.75. We like this level here, 5.75. And this will be minus 5.75. We'd like to set Vs for a voltage of 5.75 ground to peak. Okay, and that way when we lose 7/10 across the diode, we're at 5.05. We decay down to 4.95. And we have an average. You notice the green looks almost like a DC. We're going to have an average of 5. And the last thing we need to do for this is to calculate the value of the capacitor. Okay, and for that we have the equation. V sub R is equal to V sub P over F RC. So V sub R is the ripple voltage, 0.1. is equal to V sub P is the peak voltage here, which is going to be 5.05 over frequency is 60 R is 4K, and C is our unknown. And we're going to calculate the value of that capacitor, and I'm going to leave that to you to do. Now, the spec is 100 millivolts or less. So if you calculate your capacitor value and it's not a standard value, you're going to want to round it up to the next higher standard value, not rounding it down. If you round the capacitor down, you're going to have more ripple than you wanted. Less ripple is generally better. So whatever capacitor value you get here, round it up to the next standard value, and you're going to be okay to go ahead and run the circuit. Okay, so what we're going to do now is we're going to go ahead and build the circuit and watch it work. And the things we're going to measure are the ripple voltage, and we're also going to measure the conduction angle. The conduction angle, by definition, is the time from there to there. And this is the time when the capacitor is being charged, and then the rest of the cycle from here all the way back to there is when the capacitor is discharging. And so the critical thing about the conduction angle is it's very brief. You only have this much window of time to completely replenish the charge that the capacitor lost over this time right here. And that becomes critical, especially as ripple gets smaller, the conduction angle gets shorter. So we're going to measure the conduction angle on the oscilloscope using the cursors from there to there, that delay, and we're going to see what we get for that. Okay. And then for trigonometry, hopefully you know how to solve for this point. Okay, so what we're going to do is we're going to set this up as a cosine wave. If you'd like to solve for a theoretical value of this angle right here, and we're going to say, we're going to treat this red wave as a cosine theta, and the amplitude of that cosine of the theta is 5.05, and we're going to set it equal to 4.95 and solve for theta. Theta will be your conduction angle. So hopefully you remember enough trig to divide both sides by 5.05, take the arc cosine of that, and you're going to get the conduction angle in degrees. And then in the scope, we're going to measure this interval, divide that by the period of 60 hertz, about 17 milliseconds, convert that to degrees, and we're going to compare the two angles and see how close they are. Okay, so with this, we're going to go ahead and build the circuit.